Hello, in this particular session, let us discuss the working principle of DC generators. As in the last session, we have seen some of the basic concepts related to the working principle of DC generators. That is the magnetic field, how it is the magnetic lines of flux actually it is created, the magnetic flux density, the permeability, magnetic force, magnetomotive force, and we have seen the Faraday's laws. So like this, we have seen some of the we have discussed some of the basic concepts, basics related to working principle of DC generators. So as usual, we have discussed the Faraday's laws. The DC generator works on the principle of Faraday's laws of electromagnetic induction, or which is also called as dynamically induced EMF. That means there will be a relative motion between the magnetic field and the conductor. As we know that for first law we have seen whenever the magnetic flux linked with the electrical circuit changes, an EMF is induced in it. Right? Whenever the flux gets changed, EMF induced. Or in other words, whenever the conductor cuts the flux, EMF is induced in the conductor. We have seen how it is induced, how the EMF is induced, right? And the second law, the magnitude of EMF induced is equal to the rate of change of flux linkages. At what speed the flux cut by the conductor, based on that, the magnitude of the EMF induced increases. If the rate of change of flux increases or the flux cutting increases, the EMF induced in the conductor also increases. That one also we have seen. And the direction of EMF induced, it is given by the Fleming's right hand rule. Right. So based on Faraday's laws, the DC generator operates. So now let us discuss in detail. So now if you observe the diagram, we have taken the magnetic field. So basically we know that in order to induce an EMF in a conductor, we need two things. One is the magnetic field. We have taken a bar magnet for the purpose of explanation, right? And the other one is a conductor which is wound on the magnetic material we have seen, right? So we have moved the magnet towards and away from the conductor coil. We have seen that in the last session. So here also if you observe, here also we need two things. One is the magnetic field, we can observe. The other one is the conductor. Let us analyze the same concepts with this diagram. So now you can observe the magnetic field. How magnetic field is created? You can observe the north pole of a magnet. You can observe this is the magnet, bar magnet, north pole of a magnet. So here you can observe the south pole of a magnet. So in between these two arrow mark you can observe these are the lines of force or the lines of flux, what I can call. The direction is from north to south, you can observe. Okay, so here a magnetic field is created with the help of this magnet, and the strength of the magnet actually depends on, again, the conductor which is wound on the material, the amount of current which you are passing, right, and the speed of rotation of the conductor. So here what I can tell, the strength of this magnet, the magnetic field strength actually depends on two parameters: the amount of current which is passing through the coil, you can recall that picture, and the amount of conductor which is wound on the cardboard, what we have taken in the example. So here you can observe the strength is represented by the magnetic lines of force. The magnetic lines of force, you can observe this arrow mark represents the magnetic lines of force, which is also called as magnetic flux. Okay, So a magnetic field has been created, no problem with this. And the other one is the conductor part. So here you can observe the conductor AB. You can observe the terminals A and B represents one conductor, and C, D, you can observe these two represents another conductor. A, B and C, D are the two conductors you can consider, which is joined at back end. You can observe A and C, which is joined. Okay, and in front end, if you observe these two conductors, actually it is connected to slip rings. Here you can observe C1 and C2 are the slip rings. In some textbooks they will refer S1 and S2. Here he has taken C1 and C2, no problem with the notation. You can name that one as slip rings, C1 and C2. So here if you observe the conductors, we have taken two conductors which forms a coil. At back end it is connected to A and C terminals. At the back end it is connected. In the front end of the conductor, if you observe, the one end of the conductor B, actually it is connected to slip ring C2. You can observe the line, you can observe B conductor is connected to slip ring C2, and conductor D, actually it is connected to slip ring C1. Okay, so now the slip rings, again it is placed on the brushes. You can observe the P and Q are the two brushes which is placed on the slip rings. The slip rings, actually it rotates with the conductor. As the conductor is rotated, you can observe this conductor. As I rotate the conductor, these slip rings, actually it rotates with the conductor. It slips over the brushes. It slips over the brushes and rotates along with the conductor whenever the conductor is rotated. Okay, the brushes, it is made up of carbon and it is glazed, and it is placed on the slip rings. The brushes, actually it is placed or rests on the slip rings. In turn, the brushes, you can observe P and Q, it is connected to a resistive load. You can observe P is connected to resistive load, Q brush is connected to resistive load. So this completes the loop. Okay, so you have to, by observing the diagram, a magnetic field is created with the help of bar magnets, and the magnetic field is created which is represented by magnetic lines of force, which is called as magnetic flux. The second thing is the conductor part. We have taken two conductors AB and CD, and two conductors are joined at one end, that is the back end. At front end, one terminal of a conductor is connected to C1, that is D terminal, and the other end of the conductor, actually it is connected to slip ring C2, that is the terminal B. In turn, the slip rings, it is connected to brushes. The brushes are placed on the slip rings, and the brushes, actually it is connected to resistive load. So other parameters, if you observe the axis of rotation, you can observe the axis of rotation. In the session 1 we were moving the magnetic field, but here we will move the conductor. A small change. There we were moving the magnetic field, here we are moving the conductor. The magnetic field, here it is kept constant. The magnetic field, actually it is kept constant. The conductor is moving. In session 1 what we have seen, the magnetic field was moving, the conductor was stationary. A small change, that's all, right? And here, there the conductor, the magnetic field was moving linearly, but here I am moving the conductor, I am rotating the conductor axially. There is a rotation axially. Okay, here we are rotating the conductor axially. So V represents the direction of instantaneous velocity. Here we are rotating in anti-clockwise direction. You can rotate in clockwise direction. Here it is assumed direction just for the purpose of analysis. Rotate the conductor in anti-clockwise direction. At what speed? That is represented by V. V represents the direction of instantaneous velocity, small v. Small v represents the direction of instantaneous velocity. At what speed the conductor is rotating in anti-clockwise direction. Okay. So now we have to rotate the conductor and we have to see how EMF is induced and what is the amount of EMF induced and what is the direction of EMF induced. The three things we have to discuss. So based on these concepts, let us rotate the conductor and let us see what is the amount of EMF induced. Okay, here the conductor is rotated. Here the conductor is rotated with the help of prime movers such as diesel engine, steam turbine, water turbine. In the lab we will rotate with the help of DC motors. So here it is a mechanical input. We have to rotate the conductor means how we will rotate the conductor with the help of prime movers. That is the input to this is mechanical energy we can consider. We can consider as a input is mechanical energy. The output is nothing but we will get this type of waveform. Let us see how we will get this type of waveform. AC voltage. So now let us start rotating the conductor at different instants, at different points, and let us see what is the amount of EMF induced in the conductor. What is the amount of EMF induced in the conductor? You can observe the diagram, you can observe the slide. So here the same thing, just we have considered this diagram, it has been tilted, that's all. The same diagram has been tilted. Here if you observe the plane of a coil, ABCD represents the plane of a coil which is perpendicular to the lines of flux. Yes or no? This is the lines of flux. If you observe, the plane is perpendicular to the lines of flux. Okay. Here also if you observe, just the diagram is tilted. The lines of flux actually it is represented from north to south. The plane of a coil ABCD is perpendicular to the lines of flux. Again AB represents here slip ring, small AB. Slip rings. This is the brushes, the yellow sketch. You can observe the brushes which is placed on the slip rings and connected to the load. No problem. Same diagram which is shown horizontally. Earlier it was vertically, now it has been horizontally. The same diagram, no problem. Right? So another term which has come into the picture is the theta. What is theta? Theta is the angle between the direction of motion of conductor, how you are moving the conductor. Theta is the angle between the direction of motion of conductor. I am rotating the conductor in anti-clockwise direction and the direction of matic lines of force. The matic lines of force is like this. The direction of rotation of conductor is anti-clockwise direction. So what is the angle between these two? That is represented by theta. Let us start the analysis at this particular point, that is theta is equal to 0. At theta is equal to 0, that means if you observe the plane of a coil comes in perpendicular to lines of flux, and the other parameter what you have to consider is the components of velocity. Components of velocity. For understanding that, let us observe this slide. Here if you can observe the components of velocity, you can observe. So here the plane of a coil, this is north and south pole, matic lines of force is represented at theta is equal to 0. I am analyzing. So if you observe the components of velocity, this arrow mark and this arrow mark actually represents the components of velocity, the speed at which I am rotating the conductor. The speed at which I am rotating the conductor. Here you are having two components of velocity, right? You can observe this arrow mark. So here the plane of a coil, it comes in perpendicular to the lines of flux, no problem. But if you observe the components of velocity, these two comes in parallel to the lines of flux. It slides over the matic lines of force. That means there is no angle between the components of velocity and the matic lines of force. Therefore, I can call this one as theta is equal to 0. Theta is equal to 0. There is no angle between the components of velocity and the matic lines of force. The plane of a coil is perpendicular, no problem with it, no doubt. The plane of a coil ABCD, the plane of a coil if you observe that is perpendicular to the lines of flux. But if you observe the components of velocity, it is comes in parallel to the lines of flux. There is no angle. Therefore, I can consider this as theta is equal to 0. Therefore, the flux, it is not cut by the conductor. If you observe theta is equal to 0, at theta is equal to 0, the components of velocity does not cut any magnetic lines of flux. Therefore, what is the EMF induced? EMF induced is 0. According to Faraday's laws, when EMF is induced, according to Faraday's, when EMF is induced, whenever there is a change of flux, whenever the flux cut the conductor, at that time the EMF is induced in the conductor. But in this particular instant, no flux actually it is cut by the conductor, because the components of velocity comes in parallel to the lines of flux. Okay, therefore I can start the analysis. What is EMF induced? It is 0. It is 0. Now you can rotate the conductor by an angle 45 degree, let us assume. Now rotate the conductor by an angle 45 degree. Now you can observe this diagram B. So whenever the conductor, this is first instance, theta is equal to 0. Now I have rotated the conductor, you can observe at theta is equal to 45 degree, you can assume. Theta is equal to 45 degree, you can assume. Okay. Now the plane of a coil and lines of flux, if you observe, whether it is parallel or perpendicular, I cannot tell. It is diagonal. It is neither parallel nor perpendicular. The plane of a coil is neither parallel nor perpendicular, which is diagonal to the lines of flux. Which is diagonal to the lines of flux. And if you observe the components of velocity v, you can observe this is v and this one v, if you observe, which is also diagonal. And if you resolve this component, you will get two components of velocity, that is v sin theta and v cos theta, you can observe. One is v cos theta, this one is v sin theta. Because it is diagonal, neither parallel nor perpendicular, which is diagonal. The diagonal component, if you resolve, you will get two components of velocity. One is horizontal component, one is vertical component. If you observe this horizontal and vertical component, therefore I can tell the vertical component, that is v cos theta, comes in parallel to the lines of flux. Therefore I can consider v cos theta is equal to 0. Because of this v cos theta, no EMF is induced, because it is in parallel to the lines of flux. And if you observe v sin theta, which is perpendicular to the lines of flux, therefore maximum flux actually it is cut by the conductor because of this component, which is perpendicular component. So now what I can tell, at theta is equal to 45 degree, that means theta value, it is in between 0 degree and 90 degree, has taken 0 to 90 degree. Anywhere you can take, but where we have taken 45 degree, you can assume. At 45 degree, what is the amount of EMF induced? The EMF is induced due to two components, that is v cos theta and v sin theta. The v cos theta comes in parallel, you can neglect, consider v sin theta. Therefore, what is the amount of EMF induced? It is, let us assume E1, or some amount of EMF is induced at theta is equal to 45 degree because of v sin theta component, if you observe. Okay. So now we have seen at theta is equal to 0, no EMF is induced. At theta is equal to 45 degree, some amount of EMF is induced because of V sin theta component. V sin theta component. Okay. Now you can go back and you can come to theta is equal to 90 degree. Theta is equal to 0 you have seen, theta is equal to 45 degree you have seen. Now you can observe theta is equal to 90 degree. So theta is equal to 90 degree. If you observe the plane of a coil, the plane of a coil comes in parallel to the lines of flux. If you observe earlier at theta is equal to 0, the lines of flux was perpendicular to the lines magnetic field. The lines of flux was perpendicular to the plane of a conductor. Right. At theta is equal to 90 degree, if you observe, the plane of a coil comes in parallel to the lines of flux. What about the components of velocity? You can observe the components of velocity at theta is equal to 90 degree. You observe the components of velocity. If you observe this one and this one, which is perpendicular to the lines of flux, the plane of a coil is in parallel. No doubt in that. The plane of a coil is in parallel, but the components of velocity, if you observe, it is perpendicular to the lines of flux. Therefore, at theta is equal to 90 degree, all the flux, maximum flux, actually it is cut by a conductor. Therefore, what I can tell, at theta is equal to 90 degree, what is the amount of EMF induced? It is maximum, E max. E max. At theta is equal to 0, it is 0. At theta is equal to 45 degree, it is somewhere some EMF is induced. We have seen somewhere around here. Roughly we can take E max divided by 2. Roughly we can take E max divided by 2. At theta is equal to 90 degree, it is E max. It is E max. Okay. So like this, you can move on to theta is equal to 180 degree. If you observe at theta is equal to 180 degree, what is the again the plane of a coil comes in perpendicular to the lines of flux. The components of velocity you have to observe at theta is equal to 90 degree. After 90 degree, if you observe it is 180 degree, you can observe 180 degree here. If you observe the components of velocity comes in parallel to the lines of flux, whenever the components of velocity comes in parallel, no flux, actually it is cut by the conductor. No flux cut by the conductor. Therefore, what is the EMF induced? It is 0. Therefore, at theta is equal to 180 degree, what is the amount of EMF induced? It is 0. You can observe this point. The E is 0 at theta is equal to 180 degree. So, while analyzing this, you have to observe the plane of a coil and the components of velocity. Here in this particular region, on theta is equal to 90 degree to theta is equal to 180 degree, if you observe, the rate of change of flux, actually it is decreasing. The rate of change of flux, actually it is decreasing. Hence, the amount of EMF induced decreases. Earlier, during 0 to 90 degree, the rate of change of flux, actually it was increasing, so amount of EMF induced increases. Whereas in case of 90 degree to 180 degree, the EMF induced, actually it is decreases, because the rate of change of flux or flux cutting decreases, so the EMF induced decreases and reaches 0 at theta is equal to 180 degree. So like this, you can analyze theta is equal to 180 plus 45. You can take 180 plus 45, 225 degree. Here he has shown for 225 degree. He has shown. Again, further, again it comes in diagonal. If you observe, theta is equal to 225 degree. This is theta is equal to 180 degree. Again you rotate further 45 degree. 180 degree you have seen. Again you rotate. If you rotate, again it comes in diagonal. Again comes diagonal. Diagonal, again you have to resolve the components v sin theta and v cos theta. Components of velocity v, again it has to be resolved into two, v sin theta and v cos theta. If we resolve this, again because of sin component, the EMF gets induced. The cos component you can neglect. So at theta is equal to 225 degree, what is the amount of EMF induced? If you consider it somewhere around here, in between Emax, negative Emax and 0, somewhere you will get here. Minus Emax divided by 2 you can consider. At theta is equal to 225 degree. And again here it increases in reverse direction. It increases in reverse direction. Because earlier from 0 to theta is equal to 0 to 180 degree, the AB conductor was under the influence of north. The CD was under the influence of south. Now it changes. The AB comes under the influence of south. The CD comes under the influence of north. Therefore, the direction of EMF induced reverses, and again it increases in negative direction because of increase in rate of change of flux. Because of increase in rate of change of flux. Again, at theta is equal to 270, if you observe. If you observe at theta is equal to 270 degree, the plane of a coil looks like this. The plane of a coil comes in parallel to the lines of flux. The plane of a coil comes in parallel. What about the components of velocity? Perpendicular to the lines of flux. Therefore, what is the amount of EMF induced? It is Emax. It is Emax. Okay. So at theta is equal to 270 degree, maximum amount of EMF is induced in negative direction, or the opposite of the first half. Again, you can consider at theta is equal to 360 degree. At theta is equal to 360 degree, again the plane of a coil, you can observe the instance comes original position. Theta is equal to 0, you can remember, you can recall, comes in perpendicular, right? Again, the lines of flux, if you observe, it is perpendicular to the plane of a coil, but components of velocity, if you observe, comes in parallel. Therefore, no flux cuts. Therefore, no EMF is induced. Therefore, what is the EMF induced? It is 0. It is 0. Again here, from theta 270 degree to theta 360 degree, the amount of flux or the EMF induced, what you can observe, it is decreasing, because the rate of change of flux linkages or the rate of flux cutting decreases. Therefore, the EMF induced decreases. The EMF induced decreases and reaches 0. So if you observe, so overall, whenever the conductor, that is the conductor means a plane of a coil ABCD, whenever it is rotated for one revolution from theta is equal to 0 degree to theta is equal to 360 degree, if you observe what is the amount of EMF induced, it is a sinusoidal AC voltage. You can observe. After rotating the conductor in the magnetic field in anti-clockwise direction at velocity v, what is the amount of EMF induced? What I can tell, it is a sinusoidal AC voltage is induced in the conductor for one rotation. For one rotation. Continuously if I rotate, therefore continuous sinusoidal voltage actually it is generated. Continuous cycles of voltage, sinusoidal voltage is generated. So up to this discussion, we have seen how a AC voltage is generated. How an AC voltage is generated. Right. Next. So this one represents a commutator, which is also called as split rings. In the diagram, what you have shown, it is slip rings. This is called as slip rings. What you have seen in the first diagram, what you have seen, it is slip rings. So here, what is the job? Just it slips over the brushes. As the name indicates, slips. Just it slips over the brushes. Thus, if we replace the slip rings by split rings, you can observe this is commutator. It is also called as commutator. If we replace that slip rings by this commutator, then we will get a DC voltage, because we are discussing a DC generator. Whatever the voltage required at the load is a DC voltage. So a commutator is placed in the place of slip rings in order to get a DC voltage. This commutator, it is separated. You can observe again the name, as the name indicates, split rings. It is splitted. You can observe two parts. It is split into two parts and separated by insulation, mica insulation, you can observe. And these are the brushes, which is made up of carbon. Okay, the commutator converts the alternating current into unidirectional current in DC generator. Alternating current into unidirectional current in a DC generator. What is the job of commutator? It converts an AC into DC. Okay, so now you can observe the commutator we have placed, instead of slip rings, we have placed split rings or commutator. So whatever the voltage which is generated in the conductor part, it is AC. You can observe the arrow mark. It is AC. So whatever the voltage we are getting in the load, it is DC. How we got? This is with the help of commutator. This is with the help of commutator. So up till now we have seen how AC voltage is generated and how it is converted into DC voltage, and what is the amount of EMF induced. Again, it depends on the rate of change of flux or the amount of flux cut by the conductor. And what is the direction of EMF induced? It is given by the Fleming's right hand rule. As we have discussed in the session 1, we have seen the forefinger, hold all the three fingers mutually perpendicular to each other, the forefinger, the middle finger, and the thumb. If the forefinger points in the direction of magnetic field and the thumb indicates the motion of conductor, then the middle finger will give you the direction of current flowing through the conductor. Direction of current flowing through the conductor. You can observe the diagram. Direction of flux, which is indicated by forefinger, and direction of motion of conductor. You can observe how the conductor is moving in a magnetic field, that is linearly. This is the movement of conductor. Now you can observe this is the direction of EMF induced, or the direction of flow of current, which is given by the middle finger. So the direction you can analyze with the help of Fleming's right hand rule. And what is the EMF induced? Again, if you go further, which is equal to BLV sin theta. The magnitude of EMF induced, it depends on three parameters. One is the magnetic flux density, that means the magnetic field strength, the strength of the magnet. Based on that, the amount of EMF induced, greater the strength, greater is the EMF induced. And the length of the conductor which is used, you can take an ABCD conductors. If you increase the length of the conductor, you can increase the amount of EMF induced. And the speed, we represent the speed of rotation. The speed of rotation. At what speed I am rotating the conductor. Right, if you increase the speed of rotation, yes, you can increase the amount of EMF induced. So, in the working principle, we analyzed how EMF is induced by rotating the conductor from theta 0 degree to theta is equal to 360 degree. And the magnitude of EMF induced, it depends on three parameters. One is flux density, one is the length of the conductor what we are using, and another one is the speed at which we are rotating the conductor in the magnetic field in anti-clockwise direction. And the third one is the direction of EMF induced, which is given by the Fleming's right hand. Okay. So based on these concepts what we have discussed, let us analyze some of the MCQs, that is the multiple choice questions. The Fleming's left hand rule, the first one if you observe is used to find. Right hand rule we have seen. If you observe the left hand rule, if you recall in the session 1 we have discussed, which is applied to the DC motors. The forefinger points in the direction of magnetic field, and the middle finger, if it gives the direction of flow of current, then the thumb will give you the direction of motion of conductor, the direction of rotation of conductor, which is given by the thumb. That means the Fleming's left hand rule, which is applied for DC motors, which is used to find the direction of motion of conductor. If you observe option A, direction of magnetic field due to current carrying conductor. The option 2, direction of flux in a solenoid. The direction of force on a current carrying conductor in a magnetic field. And the polarity of a magnetic pole. If you observe, we can take the answer C, which will give you the direction of motion or the direction of force on a current carrying conductor which is placed in a magnetic field. That is a thumb, which indicates the direction of motion of conductor. Right. The second question, if you observe, which of the following is expected to have a maximum permeability? The permeability, as we have seen, mu is equal to mu naught mu r. Mu naught is a constant, which is called as absolute permeability. Mu r is a relative permeability whose value depends on the matic material used. Which of the following materials is expected to have maximum permeability? He has given some of the materials. We have to see the values of these materials. If you know the values of these materials, we can easily tell which is having maximum permeability. If you observe, the brass has got 1.06 approximately, the copper around 0.99, and zinc around 16 to 60. When compared to all these materials, the ebonite, which is having a high value of permeability when compared to brass, copper and zinc. Therefore, we can go for answer D. According to the Fleming's right hand rule, the forefinger point in the direction of, we have discussed just now, also we have discussed in the session 1, also we have discussed the Fleming's right hand rule. It is applied for DC generators. Forefinger, it gives the direction of magnetic field, or the option B, what you can observe, that the lines of forces, magnetic lines of forces. Okay, the A, motion of conductor, that is the thumb indicates the motion of conductor. Okay, so here what I can tell, we shall go for the answer B, which indicates the magnetic lines of force or the magnetic field. The forefinger points in the direction of magnetic field. The commutator segments are connected to the armature by means of the commutator. What is the job of commutator? Which converts, say, AC voltage to DC voltage. The commutator is connected to armature conductors by means of what? He has given copper lux, resistance wires, insulation parts and bracing. Here it is the answer A. The commutator is tightly connected to the armature conductors with the help of lux, which is made up of copper, in order to overcome, in order to withstand the centrifugal forces. In order to withstand the centrifugal forces, the commutator segments, it is connected to the armature conductors with the help of copper lux, with the help of lux, which is made up of carbon. In a commutator, next question is, in a commutator, copper is harder than mica. Mica and copper is equally hard. Mica is harder than copper, and none of the above. So in commutator, the insulation material used is mica. Based on that, what we can tell, which is mica is harder than copper, we can tell, because the insulation material which is used is mica, and which protects from cascading failure of commutator and the brush assembly. The mica, actually, it is the insulator which is used in the commutator, which is harder than copper, which protects from the cascading failure of the commutator and the brush assembly. Okay, so the option C we can consider. Next question is, in a DC generator, the current to the external circuit from the armature is given through, the current which is generated in the armature is given to the external circuit. If you observe, it goes through the commutator, brushes and then to the load. So we can tell it goes through the commutator. It goes through the commutator. Okay. So whatever the current which is generated, whatever the voltage which is generated inside the armature conductors, it goes to the load through commutator and brush assembly. Therefore, here you can observe the commutator is present. So based through the commutator, it goes to the load. So brushes of DC machine is made up of, as we know that it is made up of carbon, which has got high contact resistance. Why it is made up of carbon when compared to other materials, soft copper, hard copper, he has given, when compared to other materials, the copper has got high contact resistance, which is having less friction losses, low friction losses, and it has got ability to resist arcing. Okay, based on these parameters, it is made up of the brushes. Actually, it is made up of carbon. The material of the commutator brushes, actually, it is made up of is generally carbon. What you have seen, it is made up of carbon when compared to other materials. If you observe mica, copper, and cast iron, the other way he has asked the materials of the commutator brushes. Actually, it is made up of carbon, since which has got a high contact resistance and low friction losses, and got a ability to withstand the arcing. Therefore, the commutator brushes, it is made up of carbon. The insulating material used between the commutator segments is normally the insulating material used between the commutator segments. If you observe, it is mica. Already we have seen. It is mica. The option C. The mica has got a good insulating property. It is a good electrical insulator and a good thermal conductor. When compared to other materials, the mica is a good electrical insulator, good thermal conductor, and which has got a high withstanding capacity, which withstands high temperature. And the dielectric stress of mica, if you observe, it is 1180 centimeter kilovolt per centimeter. 1180 kilovolt per centimeter. That is the stress. Dielectric stress. The voltage which the insulator withstands. What is the amount of voltage? The maximum voltage which the mica withstands, it is 1180 kilovolts per centimeter. The dielectric stress. Therefore, the insulating material used for commutator segments is mica. The next question is, if B is the flux density, L is the length of the conductor, and V is the velocity of the conductor, then what is the amount of EMF induced? Directly we can tell, which is equal to BLV. Sin theta we have seen, but here he is rotating the conductor linearly. If it is axially, then the theta will come into the picture. If you rotate the conductor linearly, then the theta will not come into the picture. Therefore, it is directly depending on B into L into V. B into L into V. B represents the magnetic flux density, L is the length of the conductor, V is the velocity, the speed at which I am moving the conductor. So the answer is A. So if you recall the concepts of this particular session, we have seen the working principle of DC generator, how AC voltage is generated in the armature conductors based on Faraday's laws, and how that AC voltage is converted into DC voltage with the help of commutator, also called as split rings. And then the direction of EMF induced, the direction of EMF induced, or the direction of flow of current, it is given by Fleming's right hand rule, which is applied for DC generators. And also we have seen the magnitude of EMF induced, it depends on three parameters. One is the magnetic flux density, E is equal to BLV sin theta, the magnetic flux density, the length of the conductor which we have taken, and the speed at which we are rotating the conductor. Based on these parameters, the amount of EMF induced, it depends on. So based on these discussions, let us end this particular session. Thank you.